This is the fourth video of a multiple part series of a problem set that, again, I've given to my class. If you're in that class, you have a copy of it. If you're not, just copy the screen before I start writing or before I start marking it up. Okay, what about this first problem here? Here we see that there's two ketone groups in one molecule. This is more than likely an intramolecular aldol. Again, there's a base that sort of reinforces that idea. 80 degrees C means that we're going to, in the final step, lose water and form an alpha beta unsaturated ketone instead of having a beta hydroxy carbonyl compound. All right, if we look at this one, there are a lot of possibilities. Let's identify every alpha hydrogen or alpha carbon that has alpha hydrogens. Okay, and remember that to form the alpha beta unsaturated ketone, you have to have that condition. There has to be at least two alpha hydrogens on a single carbon atom. Okay, so let's look at all the possibilities we have. All right, this carbon can connect with the carbonyl group here. We'll call this reaction A, and it's making a 7-membered ring. All right. This drawing is going to look confusing, so I'm going to do a little trick here. I'm going to change the color. Okay, this alpha hydrogen, or alpha carbon, can connect to that one. We'll call this one B, and it's making a 5-membered ring. Okay. This carbon can connect to this carbonyl, and this is making also a 5-membered ring. This carbon could connect up to here. This is making 7-membered ring, but we're going to say not possible because there's only one alpha hydrogen at that carbon. We could not do the second process, the elimination of water. Okay, so let's go back to the default color. All right, so we got three distinct aldol possibilities. In A, we're going to still maintain the 6-membered ring. We've already identified that it's going to be producing a 7-membered ring. Okay, so we have two CH2s right here, CH2, CH2. Okay, at this point we have the isopropyl group. Okay, and right there we have that. There's our carbon that has the asterisk right there. So there's aldol product A. Aldol product B. Again, the 6-membered ring there is not going to change. It's going to be fused to a 5-membered ring. Okay, so as like we see before here, we're going to have that one. Okay, and it's going to have attached to it an isopropyl group. Okay, aldol product C, let's see, the asterisk one, that's the one where I removed the proton right there. Aldol product C is going to be also a 5-membered ring. Okay, and CH2, then our asterisk. Okay. All right, and we have that, right? Okay, so there's aldol product C. A, B, and C. I've identified the asterisk one. The check would have been the original C double bond O, the other C double bond O carbon. Okay. All right. Which of these are we going to obtain? Okay. Well, a 5-membered ring and a 7-membered ring are very similar thermodynamic stability. If you look at the energies of ring sizes, they were pretty similar. The amount of strain per CH2 group was the same, pretty much. What else distinguishes these? Well, this is a tetrasubstituted alkene. Tetrasubstituted. This is tri-substituted. Typically, if it's totally under thermodynamic control, we would expect to form the most substituted alkene. If the ring sizes are equal, if the ring sizes are of equal energy, we won't get any benefit that way. We do know that 5-membered rings form a lot faster than 7-membered rings. So if there's a kinetic control aspect to this, we would see primarily B and C and not A. Okay, there's another reason. That's the degree of alkyl substitution. So this reaction here is probably not going to cleanly afford one product. This is probably going to give us a mixture of B and C. Okay, again, B and C are better than A because the ring size forms more quickly and the degree of alkyl substitution is higher. If you look at, again, just looking at the double bond part of that. Okay, what's happening here? This is already a beta hydroxy ketone. These are the conditions that that cause the initial beta hydroxycarbonyl compound to convert to the alpha beta unsaturated carbonyl compound in the aldol condensation itself. Since we already have that, let's just go ahead and finish the process. So what's going to happen here is that you're merely going to do the second part of the aldol condensation, and that's the water elimination step right there. Okay. Let's look at this third one. The third one, there's 2 esters. This looks to be intramolecular. Molecular Claisen, and also better known as the Dieckmann condensation reaction. Remember that we have to have 2 alpha hydrogens, okay? So if we identify all the alpha hydrogens, there they are. We have to have, requires 2 alpha hydrogens on 1 carbon atom. Therefore, we'll be making the new ring between this alpha carbon and the carbonyl. How many carbons in that new ring? All right, so this is going to be making a 6-membered ring. Okay, so what do we get? Okay, we're going to keep the thiophene ring the same. That's a nice stable aromatic ring. Okay, it's going to be making a 6-membered ring. Okay, it's carbon 2 right here. Carbon 1 is going to have the ester group. Okay, 3 and 4 didn't really change. 5 is going to have an ethyl group on it, and 6 is going to have the carbonyl group. Okay, all right, so we get that product as the end product. There was a detailed mechanistic description in an earlier, somewhat similar example. All right, let's look at this one. This one's a very complex process. This is called the Robinson annulation. Robinson annulation, remember, we remove an alpha hydrogen, do a Michael addition. Move the anion site to a place where a 6-membered ring can form. And let's see, what else do? We did intramolecular aldol. Okay, so let's look at that series of steps applied here. All right, so this is the initial species we have. This is going to make an anion. Anion is going to do a Michael addition. Okay, I'll just draw this as a carbanion. Okay, it gives us this 5-membered ring, an ester. Okay. Oops. Crap. All right. Michael addition to the wrong carbon there. Okay, Michael addition is to this carbon. Okay, all right, so there we go. There's our initial product. We're going to have to form it on the other side so we can make a 6-membered ring. The only ring we can make there is a 4-membered ring. Okay, so this is going to produce a bridge structure. This may not be totally clear initially, but we're going to be making the aldol condensation between that position and there. Okay, so when we do the intramolecular aldol, we've done quite a few of them. We're going to have, and the 8-membered ring is going to stay intact. I'm going to draw the ketone inside the ring there. That's not the favored way to present these, but we'll do it that way anyway. 1, 2, 3, 4, 6. Okay, 1, 2, 3, 4, 5, 6. Okay, so we're going to make 6-membered ring. Okay, that may. Yeah, so we're going to continue. That's going to be there. Okay. All right, and this is now going to eliminate water from here. This is a bicyclic system, so don't look at this as being the final word for what this compound looks like. Okay, let me make a very clear double bond right there. Okay, so there's our structure right there. 1, 2, 3, 4. 1, 2, 3, 4. So I'm going to give this a better drawing here now. So it's really just an 8-membered ring fused to a 5-membered ring, bridged by a couple of carbons. This looks to be anti-Brett alkene. Technically it's not, because the ring size is large enough to hold a trans double bond. This is quite a fairly large ring system, so the okay, so we're gonna this will be kind of a strained compound, but not so strained that it can't exist. Okay, yeah, so that one's a little hard. The Robinson annulation kind of has almost every type of reaction that we know in one reaction. All right, this is an alpha halogenation. Okay, and the product of this reaction should be just putting a bromine alpha to the ketone. Okay, so that's the product there. If you're very careful, you could isolate that. That's going to produce HBr as a byproduct. You'll probably have as a byproduct products that have more than one bromine or more than one of the alpha hydrogens replaced by a bromine. All right, so what's happening here is that we are making an enol. Okay, this is now, sorry, it's not an equilibrium yet. Okay, so there was a hydrogen there. Let's just remember that. Let's put that there. Okay, normally a carbocation like this is, equilibrating with a bromonium ion. But in this case, probably not, because this is a very stable carbocation type. Okay, resonance stabilized carbocation is actually an oxonium ion. I'm not even drawing it as a carbocation because the oxonium ion is so great. Okay, what about this last reaction? Here, we're deprotonating and adding the aldol acceptor in 2 separate events. Okay, this is called a directed aldol, LDA, very strong base. It's the conjugate base of the isopropylamine, which has a pKa of about 33. Okay, so the deprotonation step is essentially irreversible. All right, so step 1 gives us the anion, and since there's no ketone existing alongside the anion under these conditions, we don't have to worry about the aldol condensation occurring right now. The aldol condensation occurs with the partner that we add. So we're going to now add the aldehyde, and that's going to produce this compound right here. which we're going to protonate. And this is going to produce this product right here. Interestingly, if you'll notice, there's two chiral centers here. This can exist as two different diastereomers. And that's actually, there's conditions that have been developed in the past few years that allow one to form specific diastereomers. This is not going to be a subject of the sophomore organic chemistry class. However, take a more advanced organic synthesis class if you want to learn that part of it. But it's kind of some very interesting chemistry behind controlling which diastereomer you form in that reaction. Okay, so this is where I'm going to stop with this one. The next problem set's going to have a different type. Next one we're going to write mechanisms, but we've kind of already written a lot of them in all honesty.